Thank you very much, and thank you for the opportunity to present my work on this prestigious conference. So in practice, a complex dynamical system often includes some time-dependent or random forcings so that they cannot be modeled as autonomous system. Therefore, the extension of the Koopman operator to non-autonomous and stochastic settings could be of great importance. And this is the topic, these extensions are the topic of this talk, with emphasis on the application of the Koopman operator-based algorithms on it. Here's the outline of the talk. First, after I briefly introduce the Koopman operator, it will be extended to the non-autonomous flow. Then I will briefly explain the main ideas of the Koopman operator-based algorithms, and then apply them on non-autonomous settings. We will see the issues that arise in different approaches. Then we will extend the Koopman operator into the stochastic framework and again apply the Koopman operator-based algorithms in it. First, the framework that we start with is autonomous flow, since Koopman operator is originally defined for autonomous flow, here denoted with phi t, and we all know how it is defined. So on the space of observable functions, the Koopman operator ut gives us the values of the observable on the trajectory at time t, provided that trajectory starts from x. In this way, the lifting from the state space, which is finite dimensional but non-linear, is done to the infinite dimensional space where the operator acts linearly. So the price that is paid is actually this infinite dimensionality. Since the Koopman operator is linear, it makes sense to consider its spectral object, of course. So now we go to the non-autonomous flow. The non-autonomous flow is usually defined by a continuous mapping S, which is defined on t times x, where x is a state space to x, t is usually a time space, time set. So we associate with this continuous mapping a two-parameter family S, which depends on tt0, and this family satisfies co-cycle property in the sense of 2, and with this actually non-autonomous flow is defined. The non-autonomous flow usually is generated actually by an ordinary non-autonomous ordinary differential equations where vector field f is dependent. So we all know that if we define the values of the non-autonomous flow as the values of the solution of the system, actually with this the flow non-autonomous flow is defined. Of course, the natural way to define the Koopman operator is to compose the observable with this non-autonomous flow. However, now the operator depends on two parameters, t and t0, and with that non-autonomous Koopman operator family is obtained. Each operator is linear, so again, we can define the eigenvalues and eigenfunctions. However, now the eigenvalues and eigenfunctions can depend on both parameters, t and t0. If we consider an autonomous Koopman operator and the differential equations as the special case of this non-autonomous, we can see that this operator lambda t0 is equal to lambda times t minus t0. So this is actually some sort of integral of lambda, which is usually defined in the autonomous settings. There is another way to define non-autonomous flow, and this is another formulation. This is Skew product formulation. In the Skew product formulation, actually, we have two ingredients. The first one is continuous mapping and family phi t, which is autonomous flow, and which is responsible for changes, temporal changes of a vector field. So it acts on the space of the parameters and changes the parameters. The autonomous flow theta has co-cycle property, and then the other ingredient, the second ingredient, is the two-parameter family, actually the non-autonomous flow, which is now defined on t times p times x. So the other parameters, the other space is actually now a parameter space. And we can look at this non-autonomous flow as mapping and as family, which depends now on parameter t and parameter p. This two-parameter family now satisfies co-cycle property over theta t. The mapping pair theta s is now called is actually non-autonomous dynamical system. Theta is driving dynamical system, and we can associate with it the autonomous flow defined on larger space, on space p times x, by using 8. So SS is autonomous flow defined on larger space, and it is autonomous semi-dynamical system, which is called skew product flow. And it is useful sometimes when the autonomous flow is periodic or almost non-autonomous flow is periodic or almost periodic. Then we can use this skew product flow definition to induce some properties of the autonomous flow, and we will see how this will be applicable in the context of using and application of Koopman operator-based algorithms. The skew product formulation of flow usually is generated in the pairs is generated by following system of differential equations, where the first differential equation, equation 9, is actually responsible for changes in parameter space, and the second one is responsible for changes in the state space. Then the first equation generates the first driving flow, and the second one actually this non-autonomous flow part. So as before, similarly as before, if we use this skew product formulation, we can also define the Koopman operator and associate the Koopman operator with it. So we obtain again non-autonomous Koopman operator family. Again, the eigenvalues and eigenfunctions can be used. And what is the purpose of this object, of these eigenvalues and eigenfunctions? It is clear here in a linear case, for example. If we take a linear non-autonomous differential equation of the form 13, it generates a linear non-autonomous flow, STP0, which is defined with 14. And in the usual point of view, this linear non-autonomous flow is actually fundamental matrix of the system. And if this fundamental matrix is diagonalizable and has simple eigenvalues, and for example, in the left and right, corresponding left and right eigenvectors, then we can associate with these eigenvalues and eigenvectors actually the eigenvalues and eigenvectors of eigenfunctions of Koopman operator. Eigenvalues are obtained from the lambda j of the Koopman operator, are obtained from this relation, and the eigenfunctions are obtained as inner product of the state space with the left eigenvector of this matrix of this linear non-autonomous Koopman operator, linear non-autonomous flow, sorry. These guys are called principal eigenvalues and eigenfunctions, and they can be used for Koopman mode decomposition. So full state observable can be decomposed by using the Koopman modes, Koopman vectors, Koopman eigenfunctions and eigenvalues, and also the evolution of the full state observable can be then determined by using Koopman mode decompositions. However, unlike in autonomous case, where only this term is responsible for temporal changes, now all the terms can be time dependent and can change in time actually the evolution of the observable under the action of Koopman operator. And first, since we want to extend and to apply the Koopman operator-based algorithms on this extension of the Koopman operator, I will first briefly share the main ideas and describe main ideas that are incorporated in this algorithm. So numerically, usually in practice, we start with we usually have the values of the observable functions and different time moment, which are here denoted with tk, which are usually with same time step. These values of the observable functions are actually the values of the Koopman operator with parameter k times delta t on this observable f, and since in the autonomous case the Koopman operator depends just on the time period on which it is applied, this Koopman operator can be obtained by composing k same operators u delta t. So we can write here u delta t to the power of k, meaning the composition we did. If we can determine the spectral objects of this operator u delta t, and we have an observable function f, which belongs to the subspace spanned by eigenfunctions or is almost in the space of eigenfunctions of phi j of this operator, then we can evaluate and envisage the values of observable f at each time moment, so also in the future time moment tk, by using this decomposition, Koopman mode decomposition, and here this term is responsible for temporal changes of the values of the observable. This is what is known in autonomous case. So what we want with the Koopman operator-based algorithm, actually we want to extract the Koopman modes and eigenvalues. Of course, we can obtain probably their approximation. We use here approach which is based on Krylov's subspace, and we use two different algorithms, but the ideas are the same. The starting ideas are the same. It's the DMD and van der Monde algorithm, and both asserts the existence of linear operator that maps a collection of snapshots one step in time. So in matrix XM, we put and collect the snapshots at x0 to xm minus 1. In ym, there are values of snapshots one step of the observables one step ahead. And then we assume that there exists a linear operator k exactly, or in a least square sense, depending on the number of rows and columns of these matrices and of the rank, their rank. And this finite dimensional approximation, this k operator k will be actually the finite dimensional approximation of the projection of Koopman operator to the subspace spanned by columns of xm. So if this approximation is relatively good, then we can expect that the Ritz pairs of the matrix K will approximate Koopman modes and eigenvalues. They are computed using Rayleigh-Ritz procedure based on Krylov's sequence of my matrix K, so that the output of the algorithm are actually Ritz pairs, here denoted with mu I and vi, so that we can extract the values lambda I, which should be approximation of Koopman eigenvalues. But the important thing is that we can determine the residuals, here denoted with eta I, the residual which are actually a measure of the quality of Ritz eigenvectors. So if the residual will help us to extract and to select only the Ritz eigenvectors, which could be a good approximation of Koopman modes, because we can obtain a large number of Ritz values and vectors, but not all of them are good approximation of Koopman modes. So the residuals will be an important tool to extract the Ritz vectors, which could approximate Koopman modes. Well, so here I quote several papers, some which are used for the algorithms which are used here. The basic algorithm, DMD algorithm, is given by Schmidt. Then some analysis and improvements are done in the second paper. The residual computation is given in the paper by Črnjarić-Žic and more, and also some other improvements which improve actually the numerical stability of the algorithm, and which allow us to determine the approximations quite satisfactory. And also the fourth paper in which the van der Monde algorithm is improved and its stability is improved. The second approach, which is used in this context, is the Hankel DMD approach, which is based on time delay coordinates. Actually, the same algorithm the same algorithms are applied. However, the observable are lifted here into higher dimensional space, which is connected with an active window. If TP minus 1 is present time, and then we define an active window of size W. So this is the window that starts with B and has W timestamps with final timestamps at the present time moment, and then we lift the observables. We take the first, for example, the first column of Hankel matrix is defined as by evaluating the value of the observable on the trajectories of length NH starting with B, and then each column is then obtained by taking but going one step to the right. So each column here we denote the column of Hankel matrix with H from 0 to MH. Then we apply the DMD algorithm to the matrices X and Y by taking the first MH columns and last MH columns of matrix of Hankel matrix, so that we hope to extract R Ritz pairs which span the range, so that the Ritz vectors span the range of H. So each column of Hankel matrix can be obtained from previous column by applying the operator K on it. So by recursion we obtain actually form 21. We obtain sort of Koopman mode decomposition to determine all the columns of Hankel matrix. So here the parameters lambda j are obtained actually by projecting the first column of Hankel matrix to the modes of to the determined modes Vj. For each k from 0 to mh minus 1, this decomposition is exact, except for the last value of k, when k is equal to mh, and then we have this residual. Actually is decomposition error, and it is actually orthogonal projection of the last snapshots onto the range of x. By taking k as defined here, we actually obtain the extrapolation, the interpolation and reconstruction of values in this part of the domain. However, if we enlarge the K, which is of course possible, we obtain extrapolation of this Koopman mode decomposition. And if this residual RMH is not too big, if it is small, and if the Ritz vectors, if we chose here only the Ritz vectors that have smaller residuals, then we can expect that with extrapolation, quite good prediction could be determined. And we will see how this Koopman mode decomposition actually acts in the prediction case. However, our first task is to apply the Koopman the described algorithm to non-autonomous case in non-autonomous settings. What can first come to our mind, of course, is to apply the algorithm by using sliding active windows. We expected somehow that we will obtain, at least locally, the approximation of non-autonomous Koopman eigenvalue, despite the fact that we know that the operator, for example, on the interval t0 to tk, is composed from k different operators on smaller time intervals. So these operators are not the same like in autonomous case. But unfortunately, this was not the case, and this is given in following theorem. Even when we take a small number of snapshots in X and Y, when applied DMD algorithm, we compute the eigenvalues, so lambda tilde are computed eigenvalues, and we showed in this theorem that the computed lambda actually depends on the derivative of the observable. And also, if in the three snapshots case, on the second derivative of observable. What does it mean? It is nicely visible for following example. If we take just simple differential equations with a diagonal lambda t, and if we take for observable full state observable, then we can show that from previous theorem that lambda tilde is actually equal to lambda t0 plus lambda dot t0 over lambda t0 plus reminder, which is delta t dependent. What does it mean? It means actually that no matter how small time step is, there is an intrinsic built-in error in the algorithm, and we cannot, and the algorithm could not gives us a good approximation, and this approximation cannot be better actually. The details and analysis of this intrinsic error that arise when data-driven algorithms are applied in these settings can be found in this paper. So we compute for different situations what the error looks like. Here is just the computation that is shows that is consistent with the previous theorem, the previously stated theorem. We have here the exact values of the exact eigenvalues, which are purely real, and when applied on sliding active windows, the Koopman operator algorithm will give us the completely wrong eigenvalue. So this approach cannot be used actually. And now, of course, first we apply the algorithm, despite the fact that we know that we will not obtain a good approximation. We consider the application of algorithm in this test example. We take oscillator with driven frequency, so this frequency changes in time. Actually, the equation 26 can be decomposed into two differential equations. In the first one, the parameters are driven, and the solution of 27 actually will give us the changes of this frequency, while then by using 27, the previous equation can be reformulated into following differential equations. And of course, we know now that this is this skew, that this system can generate this previously defined skew product non-autonomous flow. First, we apply, here we have the solution of the system, and we apply the algorithm on small active windows with size W is equal 34 snapshots. We can see here that the Ritz values that are extracted lie, for example, outside unit circle, and that they are for sure not good approximation of Koopman eigenvalues. Here we show the residuals. The residuals are for eigenvectors are quite large. So as expected, the prediction that is obtained by using this mode decomposition, which is not actually Koopman mode decomposition since the approximations are not good, is quite bad as expected. Here we show the evolution of the observables of the computed eigenvalues obtained over the when the active windows are sliding along the domain. The real, for example, the real part here should be equal to 0, but we get quite noisy values here, and similarly for imaginary part. And now we can ask ourselves, of course, what is the solution? As already said, we can look at non-autonomous system as to the autonomous with the skew product formulation, especially for the previous test example. So maybe the results given in Arbabi and Mesic might be applicable. They showed in their paper that if the observables are in an invariant subspace of the Koopman operator, the Hankel DMD converges to the true eigenvalues and eigenvectors of the Koopman operator. So what we can do, we can look at the observables on the state space F and interpret them as an observables of the skew product flow, which are defined on P times X, and these observable G are defined by using F. And then we can associate the Koopman operator to previously defined autonomous flow on larger space. And how can we treat and how can we determine the values of this operator? Actually, we can look at the columns of Hankel matrix as the values of the observable in this autonomous case, if long enough observables and if long enough trajectories are taken into account. And when we apply the algorithm on the Hankel matrix, which belongs to the large active window, so the active window which consists and which takes into which consists of the state in which all the disturbances we want to capture with our algorithm, with our dynamical system are taken into account. In that case, the Koopman operator based algorithm will gives us the we hope that it will gives us eigenvalues and eigenvectors which are good approximation of Koopman operator. And here you can see the results when we apply the algorithm to the windows of size with 340 times 10. We extract here the 70 eigen Ritz values, but we chose by using residuals. We select only those for which the residuals is of eigenvectors is smaller than some threshold. For we take here, I think, 10 to the minus 3. And we select only eigenvectors so we select only eigenvectors as modes which have small residual. Here we obtain R is equal to 18 such eigenvalues, despite the fact that initially we get 70 Ritz vectors. If we use these only selected modes, in the Koopman mode decompositions, the prediction that is obtained for 200 steps is quite good here. And so we concluded from that spectral decomposition was quite satisfactory. We applied also the algorithm in another test example, on more realistic test example, where we simulate a human cardiovascular system by using mathematical model, which consists of 21 delay differential equations, and we apply the Koopman model decompositions on large active windows with 900 time steps. And we determine the prediction for the same number of time steps. And we can see that by using the previously described procedure, we obtain quite good prediction of the system for the same period of time. Here you can see the eigenvalues, the Ritz values that are obtained from the algorithm. There is 300 of Ritz values because we use Hankel matrix of dimension 600 times 300. But we extract and select only those for which the eigenvectors have small residuals and use them in the prediction. The same is true for the other part of the algorithm of the simulation. However, the simulation of in the second part of simulation, the more irregular values are obtained, so that the prediction is worse than in the first part of the simulation, but still we think it is quite useful. And here is the change, here we present the values, real and imaginary part of eigenvalues, which are determined for sliding active windows. So we determine them in time. And now we come to the other extension, to the other part. So we want to extend the Koopman operator and consider it in the stochastic settings. Actually, we start with random dynamical system S, which consists of two ingredients. The first ingredient actually model the noise. It is described by driving flow theta, which is now defined over the probability space, while previously in non-autonomous case, theta was responsible for changes in the parameter space. Now it is responsible for this noise disturbance. We suppose that theta t or theta t are measurable and measure preserving, and that satisfies co-cycle property, of course. The other part is model of evolution. It is defined by measurable mapping S, to which we associate the two parameter family ST omega, which satisfy co-cycle property over theta t. So this is similar as in autonomous case, but the ingredients and the disturbances are different actually. For each x, ST omega x is actually a stochastic process. So with we can associate a Koopman operator to the observable f, again as a composition. However, here we do not take only the composition of the observable and the values of the flow on the trajectories, but we average the values of the trajectory of the observable on the ensemble of trajectories. So we take expectation. With this, we obtain stochastic Koopman operator family. However, in this most general case, there is no this family has no algebraic structure. To obtain some specific algebraic structure, we have to use some additional assumptions. We present here three main types of RDS, which according to the book of Arnold, the first one are discrete time RDS, which the values of this RDS are obtained as solutions of random difference equations. The other type are continuous time RDS, which are actually generated by random differential equations of the form 33, where noise enters into the system as the parameters here as the parameter here, and is denoted by theta t omega. It is sometimes called real noise. The ensembles of trajectories, which are actually values of this RDS, are given by 34. And the third type, which can be actually considered as a subtype of the second one, but has some specific properties, therefore it is considered usually as third type, is continuous time RDS, which are generated by stochastic differential equations of the form 35. Here the noise enters into the system as an additive disturbance modeled by Wiener process. Theta t, sorry, do you have, oh, sorry, okay. Theta t is defined here as Wiener shift and tracks the increments of Wiener process in time. The solutions are given by 36, where the last integral is actually Ito integral. Of course, since the stochastic Koopman operator is linear, as before, it's natural that the key object of the analysis are its eigenvalues and eigenvectors, and they are defined here with 37. In the general case, the eigenvalues and eigenvectors cannot be determined easily, but in the linear case, we can extract at least the principal Koopman eigenvalues and eigenvectors, at least under the assumptions that the corresponding linear random dynamical system is diagonalizable. And this is stated in the following four propositions, but I will just show you and skip because the situations are is actually the similar like in autonomous case, and in non-autonomous it has some specific, there are some specific details which arise from stochasticity part, but actually these principal eigenvalues and eigenvectors are defined in are obtained in the similar way as in that case. The second proposition actually treats the eigenvalues and eigenvectors for the case when the RDS is generated by this random differential equation, and similarly the Koopman mode decomposition as in autonomous and non-autonomous case can be determined. The third proposition treats the stochastic, the random dynamical system generated by stochastic differential equation with additive noise. And this is interesting case, since if matrix A is diagonalizable and has simple eigenvalues lambda j and eigenvectors, then the eigenvectors, eigenvalues of the Koopman operator are of the form lambda j times t, like in the autonomous case, and the Koopman eigenvectors, the eigenfunctions are not time dependent anymore, because all eigenvectors of the corresponding linear random dynamical system are constant and does not change in time. And when we have multiplicative noise, the situation is similar. However, the proof actually is a bit different and follows from the random dynamical system and its solution. And now we come to the problem of applying the Koopman operator-based algorithm on our stochastic Koopman operator family to evaluate the eigenvalues and eigenvectors. And it turns out that, like in non-autonomous case, it will be great, as in autonomous case, it is necessary to have the operators, stochastic Koopman operators, that depend only on the time period on which the operator is applied, and are not does not change in time. So we want to have the operator that are for the same time period does not change in time. Actually, it turns out that this requirement is equivalent to homogeneous Markovian property of random dynamical system. What does it mean? It means that the stochastic process, which is generated with RDS, should have Markov property, and this is stated through the famous Chapman-Kolmogorov equations, which are here written in the form of equation 50. If the Chapman-Kolmogorov, if the RDS is homogeneous Markovian, then the stochastic Koopman operator actually satisfies the semigroup property. So we will focus on the RDS for which the stochastic Koopman operator actually satisfies the semigroup property. When it happens, this happens, for example, in the case of discrete RDS with independent identically distributed increments, and in the continuous time RDS which are generated by an autonomous stochastic differential equations. And we will only focus on the second ones. If the RDS are generated by the following stochastic differential equations under some regularity assumptions, also the generator exists, and this generator is given by 52. Actually, you know that this is Beckford-Kolmogorov. This is Beckford-Kolmogorov operator. If the eigenvalues and eigenvectors of this operator are known, also the eigenvalues and eigenvectors of the Koopman operator are known because they follows from the spectral mapping theorem. And now we come to the application of this Koopman operator based algorithm. If we suppose that the stochastic Koopman operator family satisfies semigroup property, we apply the algorithm of the xm and ym of the following form. If the xm, we take the value of the observable at the multiple initial conditions, for example, and in ym, ym is determined, is collection of expectation of the observable over the trajectories of length k here. So we take some averages over different trajectories of length k. By applying the Koopman operator based algorithm on matrices X and Y of this form, we expect to obtain the approximation of Koopman eigenvalues and eigenvectors. Here I quote several papers in which also the numerical approximation of transfer operator are considered. The first test case is simple linear case, which the stochastic differential equations, which generates Ornstein-Uhlenbeck process. And if you know is smaller than 0, the eigenvalues are also of the form n times mu in deterministic case, and the eigenfunctions are of the following form. In the stochastic case, the eigenvalues, according to proposition 3, stay the same, but the eigenfunctions are different, and the eigenfunctions are Hermite polynomials. If we apply the algorithm by using the DMD RRR algorithm, by applying it on observable functions of the following form, we take only power of x, then we can see in the second row that we obtain quite good approximation of eigenvalues. Here with blue plus is the exact eigenvalues are plotted, and those that are obtained by the algorithm are red dots. Here again the tool with residual is taken into account to extract only those Ritz values that are good approximation of Koopman eigenvalues. And just fastly, similarly as previously in autonomous case, we can apply the DMD algorithm also on Hankel matrix. Here we define stochastic Hankel matrix in a bit different way. Actually, the columns in the columns we put the average value of the observable over the trajectories. In our paper from 2020, we proved that if phi is ergodic and under some additional assumptions, then the stochastic Hankel made DMD algorithm will converge to the true eigenvalues and eigenvalue functions of the stochastic Koopman operator. When we apply in the
we are at 45 minutes, so.
Just the results, so we can see for Stewart-Landau equations that we get at least here the first few eigenvalues approximated quite well. And the second test example refers to the two-dimensional stochastic differential equations. Here we have the results where the exact eigenvalues are compared with the approximated eigenvalues. Here for observable functions, we take the monomials of these specific orders, and we can see that we use two approaches, especially in the first one, quite a good approximation of eigenvalues are extracted and they are determined on the whole grid. So thank you for your attention. That was what I want to show you.
All right.
Thank you.
Thank you. Let's do just one quick question because we're right at the brink of time. If anybody has.
Sorry.
So
yes, please go.
Is it me or I don't know?
Yes. Yes.
Okay. Thank you for this talk. Just a question related with the Ornstein-Uhlenbeck that you use as an example. Mm-hmm. The Ornstein-Uhlenbeck process described the ground state of the quantum harmonic oscillator. So did you check the relation between your result and the usual ground state of the harmonic oscillator?
Yes, of course, I check that.
Okay. And is it consistent? Do you
yes.
find? Okay, if you take the second excited state, which is also homogeneous, but it has a node, can you say something?
Can you repeat the question? I think I didn't.
If you take the, not the ground state, but the first excited state of the harmonic oscillator, there is another Markovian process associated with it as a node, a zero. Can you say something with your method?
I can actually answer, Nelly, if I have a thought.
Okay.
I have a thought, but you go. Do you want to go ahead first?
No.
Let's say Igor, yeah. I'm not sure that.
So that's actually a really interesting question. We didn't try, but it's entirely possible to get eigenvalues because, as you say, there is a correspondence, right? So yes. It's entirely possible to get eigenvalues. That's something interesting to try, I think. Yeah, you're absolutely right. For the first ground state, the eigenvalues are correct, and as Nelly said, check it out. But we were not thinking about quantum problems when we were doing this.
Yes, but
that's true.
Like this one.
Yeah, no, you're absolutely right. Actually, maybe if you could send us some literature where people tried to compute the first excited state, that would be very useful.
Yeah, that would be great. Yeah.
Okay.
That would be wonderful. Yeah, thank you. Because it could be useful in that context. We just didn't think about it.
Good. Thank you.